Dark matter is something invisible with a large mass, which surrounds galaxies. It is such an important part of our universe, but it's so hard to discover anything about it, especially because it's invisible. But if we cannot see it, how do we know that it's there? There are some pieces of evidence that prove its existence, and this time I would like to talk about one of them. Gravitational lensing is a property of light which allows it to bend around objects with large mass. One example is the image shown on the right. It is called Blue Cluster. In the image, there are two pink galaxy clusters in the middle, and no other object is visible by eye. However, scientists found out that the regions which contain the majority of mass lie outside the pink area and are invisible to our eyes or telescopes. However, they can be detected through gravitational lensing, and they are painted in blue in the image. We refer to them as dark matter halos. But what are halos anyways? A halo is a structure of dark matter which is often spherical and contains galaxies. Halos merge into each other over time, and to track their motions, we use computer algorithms to identify them. If we want to understand the importance of or the nature of dark matter, it is so important for us to know more about halos. And to study halos, the best way is by simulating them. On our next slide, Faith is going to talk about the simulations scientists use for studying dark matter halos, including the one we use for our project.
So how do we simulate halos? Well, first we need to create a dark matter simulation or an n-body simulation. And an n-body simulation is a computational tool where you can input n number of bodies, also known as particles, into a huge box. The particles move over time, and that results in the formation of groups of particles, or halos, in the simulation. I made a figure to the left, which shows the evolution of a simulation. So first, you start off with a box of a certain size, you add particles to it, and you evolve it over time with gravity, and eventually the particles will clump and form halos. So in order for us to simulate particles in our project, we needed to use a large simulation box. In our case, it was 300 megaparsecs. And we used Illustrious TNG dark matter simulation in order to do this. Illustrious TNG is a project that creates large simulations for cosmologists to study galaxy formation and evolution. So how do we define halos in a simulation? Halo finding algorithms are meant to define objects that make up clumps of dark matter particles, called halos. We use two halo finders to compare them, and to see what results we would get. FOF groups halos together based on their distance from each other. This doesn't require a lot of memory or computational resources, which is why cosmologists like using it. Rockstar is a halo finding algorithm that groups particles together based on their distance and direction. So particles headed in the same direction and that are close together are grouped into a halo. This results in less arbitrary halo shapes and more accurate halo groupings. The issue with FOF, as can be seen to the diagram in the right, is that FOF groups halos together that don't necessarily belong together. This halo should have been broken into two parts, as Rockstar does, because the particles are moving away from each other. And FOF decides to clump it together as one halo. This can result in halos losing improbable amounts of mass, and this shouldn't happen because mass should increase as time goes on. We looked into this issue and used mass plots and visualizations to help us understand it further. So we ran simulations using FOF and Rockstar, and we observed the formation of halos in both simulations. First, we observed the 3D visualizations and made note of any abnormalities during the halo formation. Next, we decided to look at 2D visualizations to see how FOF compared to Rockstar halos. And lastly, we created mass plots to quantify our research and calculate a relative percentage error for FOF and Rockstar. And Kiki will be talking more about the visualizations we did.
So here's the image of the largest halo in the simulation. When we first found this halo, we said, wait, this looks like a Pokemon. So we decided to call it the Pokemon, and we have been calling that way for a year now. See, there's a head, body, tail, and even a little bit. And here are some 3D visualizations of the Pokemon that we created ourselves using specialized Python module. The left GIF is showing the evolution over time. If you pay close attention, you will see that the tail of the Pokemon appears at the very end, which is very strange and unphysical. The GIF on the right is showing the last stage of the evolution of the Pokemon from different angles. And although it looks like there are 3 separate halos, the head, the body, and the tail, FOF group is grouped as one halo. And that made us question if the FOF algorithm was accurate. And for this reason, we decided to compare it with the Rockstar algorithms. And here's the comparison of 2 grouping methods. Rockstar halos are shown as white dash circles, and FOF halos are colored dots. If you take a look at the image on the right called Snapshot 99, you will see that FOF groups the Pokemon as one halo, but with Rockstar, it is broken down into 3 different halos. With time, the sizes and the shapes of the Rockstar objects are a lot more stable than the FOF ones.
So after looking at the visualizations, we decided to make mass versus time plots. So we only plotted halos that lost large amounts of mass over a short period of time. This behavior is again unphysical because as time goes on, we expect halos to gain mass. And if the halos gain or lose improbable amounts of mass, this is most likely due to an error in the halo finder. And if you look to the plot on the left, FOF has a lot more unphysical halos being plotted, which means that it has a higher % error than Rockstar. And after comparing these 2 halo finders, we found that FOF has about 22 times more unphysical halos than the Rockstar algorithm in our sample. So the Rockstar algorithm does a lot better when it comes to defining halos. So why is this important? What does the level of error matter? So scientists are now gathering data from sources that have a sub-percentage or below 1% level of error. So gathering data from a source with larger error will lead to inaccurate conclusions. FOF exhibits more systematic errors, so its results can't be fully trusted. So we came to the conclusion that cosmologists should instead use the Rockstar algorithm for more accurate results, if they have time and if computational expense is not an issue. So thank you for listening to our presentation. We had a lot of fun participating in the SRP program this year, and we definitely learned a lot. Also, thanks to Boreana, our mentor, who worked with us this year. She taught us a lot and was very patient when she was teaching us all this new info.
I want to say thank you again to Boreana for her support, because she helped us so much with connecting our ideas, and we got to do all the things because of her support. And at the end of our project, we created a website. If you click on it, you will get to learn basic stuff about astronomy and programming, and also about our project in more detail. I've also posted the link on the chat in case you're interested. Also, Faith created an amazing app, so she's going to talk briefly about it.
So our app basically synthesizes all this information for you. You download it and you can get an intro to astronomy, or you can explore different things. You can learn about solar mass, and you can explore images and just learn more. Yeah, thank you.
Thank you.
Thank you, Kikyo, and thank you, Faith. That was wonderful. I wanted to ask, what is the state of this app that you made? When will people be able to download it from the Apple Store?
It's actually available right now. So if you scan the QR code on the screen, it should send you to the Apple Store, and you should be able to download it. Or you can search Learn Astrophysics. You should be able to get it.
That's incredible. Thank you. All right. Okay. So we have some questions. From Jonathan Green, we have, how are you able to tell the loss of mass over time?
That is a good question. So when we were trying to track the halos, the simulation that we were using actually gives us information back on the mass of the halos. And this sort of created a problem because we had to track halos over time. So they would constantly be losing mass, but the simulation itself would only rank the actual halos in order of like which one's larger and which one's smaller. So we had to constantly like track our Pokemon halo, for example, throughout the simulation and the different snapshots.
Great, thank you. Bridget O'Rourke says wonderful job, and asks, how did you decide to focus on halos for your research project?
Oh, Kikyo, would you like to?
So our mentor is also working on the grouping methods for halos, and because she's also thinking about how can we make the better grouping methods, we thought that it would be nice to have like the proof of like which one is better first. And and also when I first joined this program, I was really interested in visualization, and so I thought that it was really cool to be able to visualize things.
Thank you. We have a question from Felix Brasana asking, almost philosophically, I think, can you tell if we are part of a halo/subhalo?
I feel like scientists could definitely tell if we are part of a subhalo or halo itself, because halos are just like groups and clusters of galaxies. So our solar system's definitely in there somewhere.
Cool. We have a question from Doug McGlathery saying that it sounds like Rockstar is clearly more accurate than Friends of Friends. Is there any reason to use Friends of Friends when doing this kind of work? And I'm sure this is something you yourselves were battling with.
So FOF is typically used because it doesn't require as much memory or storage, and it runs a lot faster than Rockstar, which is why we were using it to originally test our hypothesis. But Rockstar, it just requires more memory, which is why people don't use it as much. So I guess if you're like running low on time, then you would definitely use FOF, whereas if you have more time, you'd use Rockstar.
Thank you. I'd like to invite anyone who's watching to press the link you'll find in the chat to automatically download this app that Faith and Kiki worked on. But we have a bunch more questions, so I'll ask another one from David Figueroa. Faith and Kiki, what are the next steps for you with the work on halos?
I think that one of the things is to figure out like how we can. I think one of the things is to figure out like another methods to group halos faster and more accurate. And I think that a lot of scientists are working on it. And because I think that like although people know that FOF halos, Rockstar is more accurate than FOF, people still use it because FOF works much faster. So I think that once there's a method which people can use it faster but also more accurate, then that would be the best thing to do.
I've got a question for you, Faith. You came in with quite a bit of coding experience. I think you were our most expert coder at the beginning. How was it like to join a program and try to apply all the things you learned about coding to, the secrets of the universe?
It was cool. I had learned a lot because before I joined this program, I actually didn't know much Python at all. And being in this internship allowed me to like expand upon like the knowledge I already have. So I was able to use Python to actually like run the simulations and to track halos across the simulations. And that was very interesting. And then I was able to build the app to help with our research as well. And I think just being able to like be here and like learn more about coding, it was good.
Thank you. Thank you to Kikyo and Faith for a wonderful presentation and for your extraordinary work on this. We're now going to move on into our final theme of the symposium.